Yeah, exactly. And so if they're the recursive yeah. Are you coming to us?
Is there a microphone, Philippa?
Yeah, it's just.
Oh, this? Oh, there's nothing to hook up.
Yeah, it doesn't seem to be a walking microphone.
That's fine.
You might have to carry karaoke. Get started. Okay, guys, the session is going to get started, so please find your seats. Are you at the hotel? Okay, yeah, we're just hoping to get like that door closed.
Okay.
Like, yeah. All right, cool. Thanks.
It was right here being.
Do you want me to recommend my giving my little spiel for a moment?
Okay.
All right. Okay, we're starting again, and I was going to just give a moment of welcome from the IETF. I'm Allison Menken, the IETF chair. And the reason I actually wanted to do this, because you got a great intro from Sharon this morning about why we're here, is to ask how many people who are here are going to be going to a research group or a working group later in the week. Looks like most of the room. Yay. Okay. Well, so we were very hopeful that would happen, and we very much want to have you participate in both the IETF and the IETF. So if you have any questions about processes, please feel free to talk to me. I'm also a longtime IETFer. Let me turn it over to our session chair now, and enjoy the afternoon.
Thanks for the warm welcome. First off, we have Manya Gobadi, who was at Microsoft Research and who will be joining MIT as faculty this fall.
Thank you, Philippa. Hi, everyone. This talk is about thinking beyond binary failures in network. So when we think about network equipment like links and routers, we normally think of them as having a binary state, like on or off or up or down. And what I want to tell you today is that there's actually a rich world that exists in between. And if we embrace that world, then there's a lot of benefits in terms of efficiency that we can have. But first of all, why do we care about having efficient networks in the cloud? The idea is that computing is in fact shifting to the cloud. With the existence of Internet of Things and machine learning algorithms like autonomous driving, there's a flood of data-intensive workload that is headed to the world's data centers. And in fact, it's predicted that the cloud data center traffic is going to grow to up to 15 zettabytes in just 3 years from now. So as part of this significant change, we're building the cloud infrastructure sort of like a new exercise. We are building data centers across the world with massive compute power, and we're using fiber optics cables to interconnect these data centers to each other under the sea and across the mountains, right? But connectivity is extremely important in the cloud infrastructure. And so there's a lot of redundancy to make sure that the network is always connected. And what I want to tell you today is that there's also a lot of inefficiencies and waste in a way that we're building the cloud infrastructure. And some of the lessons that I'm going to talk about are kind of applicable to the way that we're building the internet itself. So one of the key factors that impact the efficiencies of networks are link failures, right? Link failures are important in terms of capacity provisioning, which means that how much capacity are we going to put in our network when something fails so that we can serve the rest of the traffic. Another factor that link failures affect is traffic engineering. Traffic engineering means once you build a network, how are you going to route traffic during failures. These two feed each other and they inform each other as well. So the talk is about analytics and optimizations to improve the efficiency of the cloud by making link failures not be binary events. What do I mean by that? Let me just give you a high-level idea of the talk. What I'm showing here is that the quality of a typical optical signal in the network. The green region is where the link is up, and the red region is where the link is down, okay? So the state of the link is binary, but when you look at the quality of the signal, it actually has a rich behavior. It's not a binary variable. And so I'm going to show you that this impacts capacity provisioning, it impacts availability of the links, it also impacts traffic engineering. And so the high-level idea of the talk is that we advocate for links that have adaptive capacity and adaptive reliability levels. But okay, why hasn't anybody done this before? Because it's kind of challenging to do this. First of all, we have to understand the optical layer characteristics. A lot of the design that has been done before are based on worst-case assumptions with lab experiments. And this is the first time that we're looking at the quality of optical signals in the wild for a long-term study. Secondly, we need some sort of a reconfigurable hardware that is capable of switching between different variables. And we need an infrastructure that does all of these measurements, right? Third, this is a significant change. The way we build networks is that we think of failures as the failure happened or it didn't happen. So we need to revisit some of the IP layer resource optimizations algorithm if we were to think about failures as something that is not a complete failure, but it's a change of capacity, for example, or a reliability level. But what I want to show is that, what I want to convince you of is that once we enable adaptive links, it's going to be pretty impactful. We show that we can get 70% higher link utilization, higher network capacity if we have adaptive links. We can also have 25% fewer link failures. So the talk is about leveraging analytics and optimizations to enable adaptive links in the cloud. And I'm going to show how this idea applies to wide area networks with having variable capacity links. But somewhat of a similar idea is also applicable to data center networks as well. So I'm just going to focus on the wide area side. What's a wide area network? It's a network that interconnects major cities together. It's basically the workhorse of today's cloud services. And most of the major cloud service providers like Google, Microsoft, Amazon, Facebook, they are using fiber optics cables to interconnect these major cities together. But it turns out that putting fiber under the ground and over the mountains and whatnot is kind of a laborious task. So fiber is expensive and a scarce resource, right? So the large-scale study of an operational optical wide area network that we've done is through Microsoft's wide area network in North America. This network contains of optical cross-connects. These are the devices that sit in major cities, and they convert the optical and electrical signal to each other. And then the red lines are the fiber optic links between them. To enable long reach, every 50 miles or so, there's an amplifier device that sits in between. And so this study contains 50 of these optical cross-connect devices, say in 50 major cities, about 100 of these fiber segments, and about 1,000 of these amplifier devices, okay? I want to zoom into one of these fiber links to get a better idea of what's going on. So on one side, on the red line is a fiber link, and on the two sides I have these devices, optical cross-connects. It's actually two different fibers for different paths. And there's these optical channels or wavelengths that are traveling the signal. Okay, and like I said, there's these amplifier nodes. These amplifier nodes add noise to the signal, and they can fail independent of each other. So from a router perspective, from an IP layer perspective, think of the routers are connected to the optical cross-connects, and then there's a device called the transponder. This transponder translates the signal between the electrical and optical domains. And depending the bit rate of the transponder, or the capacity of the link basically depends on the modulation of this transponder. So for example, we were studying 100 gigabits per second wavelengths or 100 gigabits per second channels that use PM-QPSK modulation. This means that the signal is programmed to carry 100 gigabits per second of traffic. Okay. In totality, picture that map of the North America that I was showing you. We were studying 2,000 channels. That means about 200 terabits per second of capacity. So typically, there's a one-to-one mapping between one of these wavelengths and one IP layer link. So every time that I'm saying a wavelength or a channel, I'm going to think of a one port of these routers or one IP layer link. What we did was that we pulled channel signal to noise ratio out of these devices every 15 minutes for about a period of 3 years, since February 2015. Okay. Let me show you how it looks like. So on the x-axis, I have time, and on the y-axis, I'm showing you signal to noise ratio. Signal to noise ratio is a standard metric to measure the quality of a signal. The higher the signal to noise ratio, the better the quality of the signal. There's also a threshold, though. The signal to noise ratio has to be above that threshold for the link to be up, to be considered up. So above the threshold, the link is up, IP layer link is up, and below the threshold, the link is down, the optical link is down, IP layer link is also down. Okay, so the signal is kind of stable, but it also has these little dips there too, right? So what's going on in these dips? I'm just zooming into one of them. You see the link is still up. It's in the green area. It's about 2.5 hours. On average, these dips last about 4 hours. And the quality has degraded a little bit, but the link is still up. Okay, so it turns out that some of this is just collateral damage caused by humans. So this is one of those amplifier huts in the Seattle area where fiber is coming up from the ground and it's being amplified, or new wavelengths are being added or deleted. What seems to be happening is that humans go into working on one of these fiber tips, but the fiber is super sensitive to head-to-head connectivity. And if somebody is opening up the cabinet door, or they're like working on something underneath, and then somebody hits another fiber, then they disrupt the connectivity. Not so much so that the link is disconnected, but sometimes they disrupt the connectivity such that SNR drops, and then after a couple of hours, they're done with their work, they come back, so somebody fixes it, and then it comes back up. IP layer doesn't see this, but the optical layer can see it. So this is the threshold for carrying 100 gigabits per second of data, okay? What I'm going to do is that I'm going to show you the threshold of carrying different amount of capacity, having different amount of capacity on this link. So see, because we wanted to avoid these dips in the signal, we chose 100 gigabits per second modulation as a fixed modulation so that we sort of not hit too many of these little dips in the link. And what I'm going to argue is that, well, what if we were carrying 150 gigabits per second of data? What if we were using a higher order modulation for this? We would have been hitting a few more of these dips in the signal to noise ratio, but we would have been carrying also 50 gigabits per second more data. Another point I want to make is look at this point right here with the circle. Normally, right now, this is a failure because the signal to noise ratio is under the 100 gigabits per second capacity. However, it's above 50 gigabits per second capacity. So it's not a total failure. I could have been carrying 50 gigabits per second of data had I had the capability of switching between these different speeds. So basically, the takeaway is that because we are thinking of failures as binary events, there is wasted capacity in the way that we are carrying data. There's also missed opportunities to keep the link up while we could have been keeping it up. And when we look at different links, all of those 2,000 different channels and whatnot, we notice that there's actually a wide difference across channels. Not all of the channels are going to look like this. Not all of them 150 gigabits per second is the best choice. And so there's the main idea that we want to advocate is to enable adaptive links. So the challenges are, well, of course, we have to quantify impact. Secondly, we have to sort of change the traffic engineering optimization algorithms that we do, and we have to have reconfigurable hardware. What I'm going to do is that I'm just going to cover the first one, the quantifying impact, and I refer you to our upcoming SIGCOMM paper this August on the rest of the details. Okay. So here what I'm doing is that I'm showing you the CDF of signal to noise ratio. Like I said, signal to noise ratio is the quality of the signal, right? So the higher the signal to noise ratio, the better. And of course, there was a threshold that I have to be above that threshold. And so this line is showing the CDF of all of these 2,000 optical channels. Okay. The median is actually pretty good. So SNR is higher than the threshold, which is good, but it's way too good. The median is 7 dB higher than what it's supposed to be. And not only that, but 99% of the time, the channel quality is higher than the threshold for 150 gigabits per second. So kind of 99% of the time, I could have been carrying 150 gigabits per second of traffic. And 43% of the time, I could have been carrying 200 gigabits per second of traffic. So this means that there's this wasted capacity across the board. Now let's think about that little dot in the unavailability region. What I'm showing here is that I'm showing the lowest signal to noise ratio at the failure event. So consider all of the failures that have happened, and I'm taking the lowest value of them, and I'm plotting the CDF of that. What happens is that anything around 2 or under 3 is sort of garbage, so throw that out. But anything above 3 means that the channel has enough signal to carry 50 gigabits per second of data. And it shows that 25% of current link failures could have been avoided had I had a way of switching to 50 gigabits per second. Okay, when we looked at all of these links together, what we saw was that availability, which is the amount of time that each of these links are spending in the green region, is also totally different. So here I'm showing the availability percentage of all of these links as a CDF, as a cumulative distribution function. And the actual number really doesn't matter. What matters is that there's a wide difference between these channels. Like there's four nines from 99.999 to 90%. And we made a similar observation in terms of time to repair and failure probability for these different links. What I'm showing here is somewhat of a similar graph, but I'm plotting the failure probability of different links. So what does this mean? This means that this would impact traffic engineering. Okay. Why? Because traffic engineering is the function, is the algorithm that is configuring the allocation of traffic on different paths, right? And if you don't understand, if you don't think about the different probabilities of different links failing, then we are making it uniform assumption. So the goal of traffic engineering is to maximize the performance while utilizing the resources of the network that are matching the current demand, right? So it's a periodic effort. It's been a subject of extensive research in prior work. But the most important thing about traffic engineering is that we have to do traffic engineering under failures, right? What I want to make a case for is that prior work optimizes for the worst case. But the problem is that we end up excessively over-provisioning the network because we sort of want to withstand shifts in traffic during failures, but there may be improbable failures. So just a quick example. If I have two cities, Seattle to Dallas, and I have 3 links between them, and then I want to select the amount of traffic that I can carry, but I want to be robust against K simultaneous link failures at the same time. Let's say K is 2. So if the top link fails and the bottom link fails, I would like my network to be able to carry the entire traffic. Hence, I'm going to carry 10 gigabits per second all the time, because even when the links haven't failed, I would like these 2 links to be bystanding as backups. And so this is what happens really in practice. I'm showing the traffic on 2 links, and on August 4th, one of the links has failed. The blue link has failed, and the entire traffic has shifted to the orange link. Okay, and so what is happening is that if I extend this graph to the left and to the right, the orange link has the capacity of carrying that much traffic, but it's not, because it's just as a standby of the blue link. So what we advocate for is that we advocate to use failure probabilities of each link to reason about the likelihood of different failure events. And so in this case, had I had these failure probabilities from the optical domain, I would have said, okay, I can just use a probabilistic guarantee about this network. I can just carry 10, 0 on the most probable link to fail, and that way I can carry 20 gigabits per second, 99.99% of the time. So given basically an uncertainty vector, I would like to come up with an allocation vector given a flow demand between these sources and destinations, such that I can say, well, for all of the flows, 95% of the time, the demand is satisfied 99.99% of the time. And I can make it statements like loss will be less than 5% of the demand 99.99% of the time. I'm going to skip the details of the traffic engineering algorithm and put everything together for you. Okay, what I'm advocating for is using per channel signal to noise ratio and failure probabilities alongside flow demands and flow routes for traffic engineering. Flow demands and flow routes are coming from the IP layer. This is how we do traffic engineering today. The per channel signal to noise ratio and failure probability is the new stuff that we're advocating for. Feed all of this to the traffic engineering optimization engine, and then we are going to determine 2 things. We're going to think about capacity of each channel in the optical domain, and we're going to think about the flow allocation in the IP layer. And so this way we are saying that the traffic engineering has to come up has to kind of co-work between the IP layer and the optical layer together. And with that, I'm happy to take questions.
Robert Groberg, Cisco Systems. A very nice talk. Thank you. The per channel SNR, I'm wondering if there might be analogs in the RF space, right? Because you're basically presenting effectively an RF space where you're getting some effective bit throughput, and one could imagine the per channel failure probability, something like that, separate from changing modulation schemes, doing error correcting.
That's a very great observation. Yes, yes. The answer is yes, and there's work in the wireless domain and RF domain. One of the differences between the optical domain and RF domain is that actually we can read SNR pretty accurately. And SNR does not change as quickly as SNR changes in a wireless signal. The measurements that I was showing you was every 15 minutes. And when we looked at within 15 minutes, the SNR actually doesn't change that much. The time scale that I'm presenting is longer. So it's kind of better actually for this.
Ask a follow-up. Have you considered changing the modulation as the course? I think you mentioned.
Certainly, that's what we're doing, yes. Right now we're changing between 100, 150, and 200 gigabits per second. Yes, so between QPSK, 8 QAM and 16 QAM. Yes. Hi.
I get Kamal Juniper Networks. It's very interesting, but one question I had after the presentation was, when you did this statistics about the 50 minutes, were the majority of failure per channel or per fiber?
Great question. Yeah. So I'm still analyzing the data. My hunch is that most of the failures are because of the failures on the transponder sides, which means per channel. But there's definitely some failures. When the amplifier fails, most likely most of the channels together fail. Or when there's a fiber cut, all of the channels together fail. So I don't have a concrete answer for that yet, but my hunch says there is significant number of failures that are happening on the transponder side, which is a channel failure.
So the follow-up question was then, in order to plan the network, I mean, obviously there's a difference whether the failure is on the transponder side, on the fiber side. So what are your ideas about if it is on the fiber side, how to dimension the network? That seems to be a little bit more challenging than if it is a single channel.
I love that question. So if it's on the fiber side, it means that the probability of failures would be a different number. We may not be able to change the capacity because things have failed. If there's no fiber, there's no fiber. But we can allocate the failure probability correctly when we are designing the network. So, a fiber in Brazil may have a higher probability of failure than a fiber somewhere in the middle of the US. And so with that, we can inform traffic engineering and capacity provisioning by just measuring these probabilities.
Thank you.
Thanks.
Hi, Rafael, University of Campinas. I was just curious about you put the consideration that you have one IP port or one IP kind of like route per fiber, like per channel.
Per channel, per wavelength, basically.
Yes. So how does that change in your algorithm if you change this radio?
If you change
this radio one by one, I mean you have
ratio.
I
ratio
see. There, sorry. Input.
I see. Well, I don't think much would change. What I was telling you was to sort of make a mental model that when I'm showing you one of these graphs, it could be one IP link, but let's assume that it's two IP links. What it means is that the capacity of these two IP links can be increased. So in the traffic engineering optimization, if you have a mapping between them, then the sort of the engine should take care of it.
Thank you.
Sure.
Rami from Case Western Reserve University. So I have a question. When you looked at per channel SNR, did you consider the distortion introduced by the amplifiers? Because the more amplifiers that the signal or the signal is going through, the more distortion that will be introduced by those amplifiers.
You mean the longer the signal goes?
Yes.
So that is true. There's a standard of putting amplifiers every 50 miles or so. So the number of segments that are longer than 50 miles is small, but I would love to have somebody to study this part for me. I haven't had a chance to look at it.
Okay, thank you.
Thanks.
Okay, so up next we've got Ram Durarajan, who is an assistant faculty at University of Oregon.
Thank you, Philippa. Hello, everyone. Today I'm going to talk about the risk of climate change to the internet infrastructure. And this is a joint work with the Barfoots at the University of Wisconsin-Madison. So, all right. So climate change is perhaps the most significant problem facing humanity today. And, when we talk to different people, they come up with different definitions, right? All of them, they refer to global warming as simply climate change. But then when you talk to the real climate scientists, they say that it is not just the global warming, but it actually encompasses a number of things that could have significant effects on the planet. And these effects could range from, drastic increase in temperatures to, having a lot of droughts and heat waves. And, all the hurricanes that we might see in the future will be more and more intense, as well as, a combination of heat waves and extreme temperatures will lead to, effects like forest fires. But one of the significant problems that we will face in the future is the increase in sea level rise. As, things warm in the planet because of global warming and other drastic effects, Arctic ice caps and polar ice caps, they melt, and they're going to lead to increase in sea level rise. And this is a slide taken from NASA. This was published in 2014. I want to point to one key point shown in the slide, which is, we know seas are rising and we know why. But the urgent questions are by how much and how quickly. All right. Since then, people have been working on a number of models in terms of understanding the impact of sea level rise on different things. And based on the model that has been developed by NASA and some of the researchers in the space, the main question we want to ask in this talk is, what is the impact of climate change induced sea level rise on the internet infrastructure? Okay. Before answering this question, we want to first look at whether is seawater actually a problem to the internet infrastructure. So what we found from some of the studies that have pursued in this place is that the entities like water, ice, and humidity, they are actually indeed threats to the fiber optic strands, and that could lead to a host of problems like signal loss, attenuation, physical damage like corrosion, fiber breakage, etc. And based on our experiences in terms of physical topology mapping over the years, we actually make two key observations. The first one is that these infrastructure deployments, even though they are all housed inside polyethylene conduits, they are not designed to be resistant to water, in the sense that they're not designed to be underwater for a prolonged time. And then most of these deployments are aging in the sense that they are typically 20 years old, which means that a combination of the observations and the prior studies actually makes us 2 points, which is the physical damages to conduits are really going to happen because of seawater, due to effects like inundation and corrosion. And this aging will only magnify and aggravate the effect of climate change and the seawater on the internet infrastructure. Okay, so how do we analyze the problem? So we take two different data sets to analyze this problem or the impact of seawater on the internet infrastructure. The first one is the infrastructure data from the Internet Atlas project, which is by far the largest repository of the physical internet data out there. So we have maps of over 1,500 service providers from which we collect the node and link information. So the node information include things like point of presences, internet exchange points, co-location facilities, submarine cable landing stations, etc. And the link details include things like long haul, metro, as well as submarine cable that connect all these submarine cable landing stations. So this is the first data set. And then to get the impact of the seawater and analyze the impact of seawater, we take the model-based SLRA data set, which is sea level rise inundation data set from the Office of Coastal Management from NOAA. So what they list is that they list all the different sea level rise scenarios in terms of different feet and the to be affected coastal geographic areas in all these coasts because of sea level rise. And they actually categorize the data into three different types. meaning high, low, and medium risk. Okay, what we see in this table below is simply the model of worst case risk that could happen over the span of this century. Okay, so in 2030 we would see about 1 feet of sea level rise according to the worst case model, whereas by the end of the century we'll see 6 feet of sea level rise in many of the coastal areas. All right, using these two data sets, we analyze the impact first. So we start with the infrastructure inundation analysis, where we fuse the two data sets using the projection and transformation tool using the ArcGIS software, which is a geographic information system that all the cartographers and geographers routinely use to do mapping. So the question we want to pose is, okay, what is the impact of seawater and the rise and inundation because of seawater on the assets deployed in many of the coastal areas? All right. So the slide here, which is going to pop up in a second, actually shows the visual overlap between seawater in many of the zoomed in parts of the United States and the internet infrastructure in those areas. Okay, the blue shades here, they are actually the incursions that's going to happen, the worst case incursion that's going to happen because of the model predicted. And the assets are shown in different colors. So red actually shows the submarine cable stations along with the cables. And the green dots, they denote point of presences, IXPs. And the black lines, they denote long haul cables. And the green lines again denote the metro fiber deployments in many of these areas. Okay, visually we can actually observe that this is a possible scenario in many of the coastal areas in the US. So let us perhaps quantify the effect in many of these areas. So what we do is we develop a overlap model using the two different data sets, and then we develop a metric called coastal infrastructure risk metric, which is used to highlight the amount of geographical overlap between these two data sets in many of the coastal areas. Okay, and we temporally assess based on the temporal patterns given in the SLRA dataset using the overlap tool, where we calculate the number of nodes and the fiber miles that overlap with the seawater incursion given by the dataset. Okay, and basically that's going to give out a bunch of patches in many of the coastal areas where we simply apply a kernel density estimate, and then that's going to emit a floating point number, which we reverse sort and then rank all the different places based on the risks. So what this graph shows here on the x-axis is the span of the sea level rise for the worst case scenario by the SLRA dataset, as well as the type of infrastructure on the y-axis in terms of the counts. Okay, and what we see from this graph here is that as high as 770 POPs and 235 data centers will be affected by seawater rise in terms of like 1 feet in the next 15 or so years. Okay, and as high as 788 POPs and 249 data centers will be affected by the end of the century based on the worst case projected data set from the SLRA dataset. So the graph here shows the similar result, but for the fiber conduit part. And x-axis again shows the span of years, and the y-axis, they show the raw fiber miles that will be affected for long-haul metro and submarine cable. And what we see here is as high as 2.6K miles of metro fiber in many of the coastal areas will be affected by worst case sea level rise by the end of the century. Okay, so these two graphs, they just look at the raw types of nodes and link assets in many of the coastal areas. Next, we actually dig deeper into the type of asset and then group them into the geographic areas and then rank them simply, which is what is shown in this table. And the raw counts of the nodes or the asset types are shown in the brackets. And as you can see, many of the economic centers like New York, Seattle, for instance, they're all going to be affected because of the seawater rise at some point. And all the nodes are actually repeating across multiple columns in this table. For instance, New York, Miami, and Seattle are carrying all the POPs, data centers, and IXP entities across the different columns, which means that there is this notion of shared risk as well in many of these areas. So the next slide here shows the same result for the link dataset, where the overlap of link assets in many of the geographic areas that is again ranked is presented here. And as you can see, New York, Miami, and Los Angeles are like present across both those columns. And here's a pictorial representation of both New York and Miami, where again the blue shades, they represent the seawater inundation in many of these areas, and the assets are shown in green and black. So as you can visually see that, a lot of metro fiber and infrastructure in these areas will indeed be underwater over the coming years. And finally, here are the top 10 providers. I would like to talk to people from this room. If one of these providers are in the room. So these are the top 10 providers who will be affected because of the deployments in many of these areas based on our analysis. So our analysis is actually very, very preliminary and then conservative in the sense that we just take two different data sets and then we assess the overlap between these two data sets. But for those of us who believe in climate change and how do we mitigate them, there are a number of steps that we should work on. And I want to talk about some of them in the upcoming slides. The first thing we want to do is expand the vulnerability assessment that we have in the study. For instance, we just, like I said, we take two data sets and then we apply overlap and then come up with a set of risk metrics. So how do we incorporate all the dynamic aspects? Like, for instance, climate change is accompanied by thunderstorms and hurricanes and earthquakes. So what is the combined effect of all these natural disasters on the internet infrastructure in many of the coastal areas? So another aspect of the problem is how do we come up with an isolation mechanism such that the coastal assets, when they get affected, they could be isolated from the inland assets so that this doesn't become a cascading failure. Finally, we also want to look at some of the impacts outside the US because, submarine cable deployments, as you can imagine, they connect different continents. So we need to have like a unified view of how things get connected across different continents. Another aspect of our mitigation is to look at ways in which, how do we integrate the traffic engineering with risk-aware mechanisms from the CAR metric that we develop. For instance, can we feed the CAR metric directly into the routing substrate so that we can redirect traffic in the face of such an outage or in the face of a combined outage like thunderstorm plus sea level rise. And we also want to assess the impact of hardening infrastructure in many of the coastal areas. For instance, if we have seawalls near all those co-location facilities that terminate near a landing station, would this help in mitigating the problem a bit? So we want to work on that aspect as well. And finally, in terms of ISP deployments, apart from considering metrics like cost and revenue and maximizing the users, can we also add another risk factor to it so that this becomes a multi-objective optimization problem for them in terms of making a risk-aware future deployment. So with this, I'd like to conclude by saying that the threat of climate change induced sea level rise on the internet infrastructure is really, really imminent. Okay, and our study actually shows that a very conservative number of 4.1K miles of fiber and about 1.1K nodes will be affected because of seawater. And this is all going to happen in the next 15 years. So all the future work that I spoke about should start today. With this, I'd like to thank my sponsors, and I'd be happy to take more questions. Thanks.
So, Tobias Fiebig, TU Delft, the Netherlands. Did you actually take a look at when it's too late for us?
No.
Not the Netherlands, but like as a community. So when is the tipping point? When does the internet drown?
No, we have not, unfortunately. But we could talk more offline.
I have a, I guess, past question. Hurricane Sandy broke a bunch of infrastructure. Were you able to put that into your model and looking at that? And I thought I may have seen that, yeah.
So you might want to take a look at this paper. So we actually look at Hurricane Sandy, Katrina, and all those effects on internet infrastructure.
Marco Davids, SIDN, also from the Netherlands. For those of you who found this talk a little bit depressive, I can reassure you there are areas in our country who are well below sea level, like 7 meters or so. So call us if you're concerned.
Niels de Noever, University of Amsterdam, also from the Netherlands. I don't see the pattern here. It's I was wondering, have you considered also turning the research question around to do research of the impact of the internet infrastructure on global warming?
That is an interesting thought, but we have not considered that.
Janai Iyengar, Niels, to your question, there was a paper several years ago, somebody else might remember better, but there was a paper by Bharat Raghavan and Hornitz on the energy consumption of the internet. It was an estimate. That might be a partial answer to your question. I'm happy to send you a link.
So with that, let's thank the speaker. Okay, so we're going from climate change to some thoughts on DNS robustness. We've got Mark Allman from ICSI.
Now I know who reads the slides. Okay, so we've been thinking about DNS for a few years, not necessarily DNS robustness per se, but sort of understanding the ecosystem. And so a couple of things have happened in the last year and a half that have sort of started me thinking about how robust the DNS system is. And so I have some sort of initial results here, nothing hugely conclusive, but some thoughts on this. So the first thing that happened was this attack on Dyn about a year and a half ago or so. Big DDoS attack on a big managed DNS provider. Probably most of you have heard about it. And so it sort of had this ripple effect, right? Dyn's customers sort of couldn't be reached because users were not able to get a mapping between the name and the IP address. So that was the first thing that sort of started me thinking, oh, wow, maybe the DNS isn't as robust as I thought. And then I drew this plot as part of another bit of our work, and this is a completely boring line. So this is 9 years on the x-axis, and this is the growth rate in the number of second-level domains in the ComNet and org zone files, and this is just what we would expect, up and to the right. The second line that I'm going to draw is the one that sort of caught my attention, and this is the number of A records that I found in those zone files. And that has a little bit of a different shape to it, right? Goes up, comes down. And so I sort of started thinking, wow, we're sort of serving more stuff with less name servers, right? And there's lots of, you can't really draw that conclusion from this plot necessarily. There's lots of more analysis that you would have to do, but I like to think of this as an objective inkling, right? This gives me some notion that there's something to look at here. And so I was thinking about sort of how robust is the DNS. And I keep coming up with sort of two answers to this question. And the first one is I keep coming back to, well, it must be good enough because I never have any problem with it. I use it every day. You use it every day. I've used it all day today. I haven't had a DNS problem all day. When my wife or my kids or my dad, and they complain about the network and I look into it, it's never a DNS issue, right? So it must work okay. But then I keep coming back to these other things, right? But perhaps there's more to it. So as I was thinking about this more, it's thought, well, how do I define robustness, right? What does it mean to be robust? And that'll make your head swim, right? Because there's a zillion different aspects to DNS robustness, right? But the one that I've been thinking about the most is sort of, can I sort of always get to an authoritative server for the record that I want, okay? So that's what I want you to keep in mind here for a minute. And I want to start here thinking about that notion with the DNS hierarchy that we all know. This is the one that I show in networking class when I teach networking, right? So this is basic stuff. But I want to think about these top two levels here first, the root and the top level domains, right? I want to think about robustness there. So this is community infrastructure. Up here we have things like lots of named replicas, right? We have 13 named root servers. So if I can't get to B root, I'll try J root or something, okay? I have lots of different things to choose from. And not only do I have a bunch of named replicas here, but I have lots of unnamed replicas, right? We use Anycast up here. Most of the roots are Anycast. So there's lots of instances of JRoot or whatever, right? So we get a lot of robustness up here at the very top of the hierarchy just from replicating things, like a lot, okay? So we can sort of always get what we want because there's always another replica there. They started reasoning about the next level here, the second level domains. And here, this is different. I went off and looked in again, the ComNet and org zone files, and 80% of the SLDs have 2 or fewer authoritative servers named in the zone files, okay? So that's a lot different than 13 root servers, okay? We know there's Anycast use down in this level. I don't know that we know how much, but we know that some of these domains are run by the Cloudflares and the VeriSigns, and they use Anycast, and that's great. And we also know that there's some things like berkeley.edu that don't use Anycast, right? So there's some unevenness to that. So we don't really know what's going on there. But, you know, sort of the high order bit for me at the second level domain is that this is where our hierarchy gets really fat. And so there's a ton of different operators implementing a ton of different policies, and we really don't know what's going on. And when we really don't know what's going on, you know, Mark's favorite thing to do is let's measure it. And so that's what I want to do. I want to measure the DNS at the sort of the SLD level and see how it looks. So to do this, I used 2 basic data sets. I used the ComNet and org zone files, and I intersected those with the Alexa list of popular websites. So I just took out everything from the zone files that pertain to one of the top 1,000,000 sites and put that in what we call a winnowed zone file. I did that once a month for the last 9 years. Okay, so we have Alexa data going back 9 years. We have zone file data going back 9 years. Just did one snapshot a month. So let's think about what we're going to look for. How are we going to define robustness? Well, the RFCs help us out here a little bit. 1034 says, well, to be robust, you should have multiple authoritative name servers. Okay, so that's at least 2. 2182 goes on to say, those name servers should also be both geographically and topologically diverse. Okay, they should be different places in the network for robustness. All right, so what does it mean to be diverse, topologically diverse? Well, you could go and you could look at a routing table and you could figure out the different places where things are attached, and that would really nail it for you. But I'm a lazy guy, and so I didn't do that, and I didn't have this data at hand going back 9 years, and this is initial work. So I picked a different method, and I use /24 address blocks to define diversity. Okay. So if two addresses are in 1/24, we know those are going to be routed to the same place in the network. Okay. So there's going to be no diversity, right? If two addresses go to 2/24s, I'm going to call that diversity for the next 10 minutes, okay? Even though we know that those 2/24s may route to the same place, okay? But we'll call that diversity as a first cut here, and we'll put a bookmark in it that says future work is to make this better. All right, so let's look at the RFCs compared to reality here. Again, 9 years across the x-axis. The blue line is the percentage of SLDs that just meet what the RFCs suggest. Okay, so two name servers, two authoritative name servers, right, in two different /24 networks. Okay, it's somewhat stable there between 45 and 50% over time. Draw a black line here. These are the SLDs that exceed the requirements suggested in the RFC. That line's sort of going up, except for these last couple points, but we'll ignore those. It's generally going up. That's good, right? And then here's a red line. These are the SLDs that do not meet those requirements, okay? That's been dropping over time. That's a good thing too. Okay, so the implications of my lazy assumption about /24 blocks is that the blue and the black lines are upper bounds, okay? They can go down if two /24s are in fact routed to the same place, right? The red line is a lower bound. It can't go down anymore, okay? But it can go up. And I looked at some data here in April of this year, and it seems that the black line is okay, out in the right spot. But the red line is low and the blue line is high. So they're growing towards each other. So the way to read this plot, I think, is sort of to add the red and the blue together and say, those are SLDs that are either just meeting the requirements or not meeting the requirements, okay? And that's about 2/3 of the SLDs. All right, so let's go back to my picture here. I want to highlight these boxes now. These are all boxes, these are all parts of the namespace that have to do with ICSI. And I just want to remind everybody, these are actually all run from the same authoritative infrastructure, okay? So we know this. Different parts of the tree here can be, in fact, running from the same pieces of infrastructure, okay? So that infrastructure exists, right? And you can't see it by just looking at the hierarchy, right? Obviously, the more concentrated we become, the bigger our problems become. So the more SLDs served out of a single name server, the bigger the problem is when that name server goes away for whatever reason, right? And we're also making juicy targets, I think, by concentrating things together. All right, so let's look at another plot here. I'm going to tell you about this plot. So what I did was for each SLD, I figured out the number of other SLDs that use the exact same name servers, okay? I draw a distribution for every month in the data set, and this is the median and the maximum of that distribution, okay? So first thing we see is, actually this is pretty stable across time, both the median and the maximum, pretty stable across time. That kind of surprised me at first. I thought, you know, sort of intuitively, as time has progressed and as the Dines of the world and the Cloudflares and whatnot, we would see some increase here in concentration, but we don't really see that too much. We see here that half the SLDs, roughly, across this are sharing the same exact name servers with at least 100 other SLDs. Okay, the biggest groups up here include 9,000 to 10,000 SLDs. Okay, so I did that. The next thing I did was I said, well, let's go back to my stupid /24 assumption, and instead of looking at just the set of exact name servers, let's look at the set of /24s that each SLD depends on, and how many other SLDs depend on that same set of /24s. So this is the same plot, median maximum of the distribution across time. And now we see that concentration is in fact increasing over time. Okay, so the maximum there has doubled in 9 years, and the median has increased by 25 times. Right here in April of 2018, half the SLDs are in groups with at least 3,000 SLDs. Okay, it was just over 100 in 2009. Okay, so we're definitely seeing more concentration in terms of edge networks here. I want to focus a little bit on the blue line up here, the top groups, and then I'll be done. So here are the top 10 groups in April of 2018. Okay, so we see that the top group includes 71,000 SLDs that all share name servers in 2/24s. Okay, and it goes down from there. There's two big ones up there. 1 and 2 are pretty big, and then they drop off pretty quickly, but still quite a few SLDs even in the last one. So the sort of upshot here is that 20% of the popular SLDs, over 200,000 there, it's 20% of Alexa's list, fall within just 23/24 blocks. Okay, so then I did one more thing, which was I ran traceroute to every one of those 23/24s, looking at the last hop router to see if any of them shared a last hop router. And wouldn't you know it, some of them do. So go back to that top group, 71,000 SLDs fall within 2/24s. The 2/24s are routed to the same place. Okay, so depends on one edge network. So we can reframe this here. 20% of the SLDs, the popular SLDs, rely on just 19 edge networks. All right. So that's pretty much what I have. I don't mean to say that the sort of DNS sky is falling, right? I mean, it's worked for me all day today. But I do think that, you know, some of this should give us a little bit of pause, right? And some of this looks like a little bit of unhealthy habits to me. You know, I'm not trying to say that concentrating our infrastructure is completely bad. There are some good reasons to do it. And it buys us some things, but, you know, it could be some costs too. So that's what I have. As with most of these talks, I guess this is sort of an advertisement. There's a draft paper there. You can grab it. There's more details. There's more results in there. And I'll take questions, or heckling is more like it here at the IETF. Oh, there's so many of you. Go ahead.
No, that's just one of me.
I know there's one of you. That's enough.
Thankfully, yeah. Well, thank you, Mark. That was a lovely talk. I'm trying to square away something in my head. The last slides that you showed, I think, collapsed a couple of points. The slide with the router, the edge networks one. I think the last slide, literally. One after that, and yes, that one. How does Anycast play into this? How do you detect when you detect the last hop?
Yeah. So I didn't say much about Anycast, except that it's sort of out there, right? And so the way I look at this is Anycast sort of breaks the network into sort of regions. So even if we have a problem here in Montreal that we can't get to these 71,000 things, right? That doesn't mean that there's a problem in Europe right now, right? So, but it's still going to be a problem for us, right? Yes. It's going to still be a pain here. So we still have a regional problem. Now, some of these things are in fact Anycast, right? I don't remember how many of the top 10. The 3 of the 4 with checks there are Anycast. And if you run traceroute from different places, you will end up at a different name server, okay? Always the same name server within the group, right? But a different name server. So there's definitely Anycast running around here, and that definitely does help, as long as, you know, you're not where the attack is happening.
Yeah, but your point is regionally, it's still concentrated.
It's still a concern.
Fair enough.
Yeah.
Thank you.
Yep.
Robert Broberg, Cisco Systems. A very nice talk. Thank you. The same last hop, I'm wondering, concentration, did you look, I'm assuming you looked at, I mean, they're probably concentrated in just a few, the big cloud providers?
Oh, sure. Yeah. I mean, the number one up there is Cloudflare. I mean, you know, number 4 is also Cloudflare. That's the only repeat in the list. But I mean, the rest of these are, you know, the GoDaddies and the VeriSigns, and you can figure out what, you know, the usual suspects.
Giovanni Moura, CIDN. I work for TU Delft, Delft University of Technology. So I work for DNS operator, and I actually did very similar analysis on that, but I never published because I got stuck somewhere. It was presented in IEPG, like I think last year. IEPG is a meeting that takes place on Sunday before the IETF. Okay. And what I found it very hard, and probably maybe something that comes across in your presentation, it's very hard to define what is robustness against what? Against the DOS, for example. If you take down, I mean, the DOS take down entire data centers, so you can have as many /24 as you want to. You know, that happened before. Sure. And another thing is, depends a lot on the market, like the hosting market, there's the sharing hosting market, and they're going to share a lot of name servers. So I found it very hard to quantify because we're talking about a layer that's very high, and it's very different from the physical infrastructure. So I got stuck and I gave up, but it's nice to see someone moving on that too.
Yeah, I agree with that, right? I think it's easier to say that something, I'm not sure if I want to say is not robust, but is, you know, looks a little sketchy than it is to say something is really robust, right? I can say, I think that 71,000 SLDs in one edge network looks a little, you know, sketchy. But, you know, if that was across 10 of them, could I say it was robust? I don't know, because you're right. There's, I mean, it's an onion, right? There's layers to this thing, right?
So just a little advertisement. We have been working on that in a different direction on the robustness of the DNS protocol itself and caching. So I'm going to present a technical report on the MapRG, the measurement session on Thursday. Maybe it might be interesting for some people that care about DNS. So.
Okay.
Hi, this is Andre from IC with my DNS.org board hat. There's going to be a DNS.org meeting in Amsterdam in the fall. And there's still the call for the papers open. So I think it would be useful to have this presentation at the DNS.org if you can come.
Okay, thank you.
Thanks.
Keith bugs me regularly too.
Hi, Brian Trammell. Happy that somebody mentioned Amsterdam in this particular line, so I don't have to. I don't really have a question, so I guess this counts as heckling. This is really interesting stuff. We in the IAB have been concerned about sort of consolidation in all of its forms and how that, you know, consolidation is really won over robustness, right? We have a lot of assumptions in the internet architecture that we're going to put something in a document that says use 2 name servers and then it will happen. So this is really, really interesting data there. It seems to me that this, especially this slide, since we're up on it, is conflating 2 things. One is the drive toward essentially hosting web stuff on cloud infrastructure, where the DNS comes for free. And one of it is sort of a drive toward actually consolidating DNS infrastructure because, you know, when you have scale, you can do it for more cheaply. Did you look at how many of the domains that are served here actually also have the A records in the same cloud provider? I mean, so is this drive here primarily just all the content's moving to the cloud and the DNS comes for free, or is this also affecting DNS?
Right. No. The easy answer is no, I didn't look at it. And the slightly harder answer is yes, we probably should.
Yeah, cool.
But,
so do that and then go to Amsterdam. Cool. Thanks a lot. All right.
Hello, David, BI. And I think this picture is very typical that give me an impression that most of the domains hosted by some kind of CDN, typically CDN company. And I once heard a talk about the monopoly of the current internet infrastructure, that most of the traffic or the services provided by the maybe top 10 companies. So maybe you can add another column that the address, the owner of the address, the company host this domain. My really question is that what in your paper or your study want to deliver? I mean, any suggestions or any future work can.
In my usual fashion, I like to understand things and measure things, and that was sort of my first goal, was to sort of start to understand this in an objective way and with measurements, and not just sort of my mental model, which is usually wrong. And so that's this piece. I don't I can't stand here and give you a solution to this other than, hey, maybe we should diversify a little bit more, right?
Okay, so time for one last question.
Olaf Kolkman from the Netherlands. I grew up 6 meters below sea level, but that was the previous talk. The question that I had, which was sort of triggered by Brian's observation, is around fate sharing. If you look at robustness and you look at the cloud providers that offer the DNS as well as the content that people want to go to, then there's a fate sharing component to that. I think it's useful to sort of tear that apart a little bit, where if there is fate sharing, obviously there's a robustness problem, but since there's fate sharing, you would say, whoever owns the content should figure that out. However, if you outsource to a DNS provider, then that fate sharing is not there, and the equation becomes a little bit different.
Right, and I agree with you. There's a paper it's an old paper. Craig Shue from WPI did a paper, maybe 2007 IMC. It's a short paper on sort of how small is the web. It's a small world. I don't remember. If you look up IMC, I think it's 2007, you'll find the paper. The web is smaller than it seems. That's right. Yeah. So they start to tackle that problem. I think it's a good problem to tackle, a good thing to understand, but I have nothing to say about it. But yeah, it's a good idea.
Cool. So let's thank Mark. Okay, so going from DNS to time travel, we've got Nita Rosen-Schiff, who is a research associate at the Hebrew University.
Thank you. Hi, I'm Nita, and today I'm going to present a work on how to protect NTP with Honus. It's a joint work with Omer Deutsch, Danny Dolev, and Michal Shapir. So NTP is network time protocol, which synchronizes time across computers over the internet. I guess you all know how major this protocol is. Many applications rely on it, such as TLS that was discussed this morning, DNS, HTTP, Kerberos, and many financial applications. In a nutshell, NTP is a client-server architecture, consists of two main steps or processes: a pull process and a selection process. In the pull process, the client sends NTP queries to the NTP servers and gets NTP responses. In the selection process, okay, maybe I will just move to that one. Okay. In the selection process, the best time sample is selected, and the client updates its clock accordingly. However, NTP is highly vulnerable to man-in-the-middle attacker, a special made to time-shifting attack. A special made by man-in-the-middle attacker who can sample the NTP response, since he controls the section between a client and one or more of the NTP servers, and can present another time sample and make the client believe that this is the best time sample and update his clock accordingly. Man-in-the-middle attacking can also impact local time at the client simply by dropping or delaying packets to or from servers. That is why encryption and authentication are insufficient. And previously, studies even consider man-in-the-middle as too strong for NTP. But why is NTP so vulnerable to man-in-the-middle anyway? So as we've said before, NTP consists of two processes, pull process and selection process. In the pull process, the client rely on a very small set of NTP servers, and they're often DNS cached, which means that the attacker only needs man-in-the-middle capabilities with respect of a few NTP servers in order to maintain his attack over time. And the NTP selection process algorithms assume that the incurrency are rare, and most of the NTP responses are well distributed around the UTC. That is why powerful and sophisticated man-in-the-middle can bypass these algorithms, and he's usually beyond the scope of traditional truth models. In order to face these limitations, we propose a modified NTP client called Conus NTP client with the following characteristics. It has provable security. We can bound the probability of successful time shifting, even made by man-in-the-middle attacker. It has a backward capability, since there is no need to change anything in the server side, and only software, limited software changes are needed in the client side. And it adds only low computational and communicational overhead, since finally we query only few servers. So in order to show how Honus protect the NTP, we need to define our attacker. So we assume that the attacker have full control over a large fraction of NTP servers in the pool, and notice that we assume that the attacker has fully control over the server themselves, and not only on the section between a client and a server. This is why we assume that he is capable of both deciding the content of the NTP and the timing when the NTP response is going to arrive to the client. And of course, we assume that he's malicious and try to make the maximal shift in the client's clock. So how Honus is built? On the one hand, we rely on many NTP servers. We generate large pool of NTP servers, 100 per client, in order to raise the threshold that is needed by the man-in-the-middle attacker. On the other hand, we query only few servers that are randomly chosen, around tens, in order to avoid overloading the NTP servers. And finally, we use smart filtering in order to remove outliers and make it hard to the man-in-the-middle attacker to contaminate the chosen samples. So informally, I will describe how a Honus client updates his clock. So out of 100 of servers, 10s are chosen at random. We order them from low to high, and then we remove these from each side and take a look at the remaining set. Then we have two questions to ask ourselves. First, if the remaining samples are close to each other, and if their average is close to the local time. If these two conditions are satisfied, then we use their average as the new client's time. Otherwise, if we fail, we resample. And again, out of 100 servers, 10 are choosing in random, they are dropping from each side. We take a look at the remaining set and see are they close to each other, and is their average close to the a client's time. If you fail, we try again and again and again until we fail 10 times, and then we move to our panic mode, which means that we query all the servers in the pool, drop outliers, and take their average as the new client's time. So first, let me present our security guarantees, and then I will describe our security analysis. So essentially, what we show in our paper is that shifting time at one Honus client by at least 100 milliseconds will take the attacker at least 22 years in experimentation. And this is when we consider a very extreme parameters. I mean, we have server pool of 500 servers, but 7 of whom are full controlled by the attacker. We also assume that we queried 15 servers per hour, and that good samples are within 25 milliseconds from the UTC. We call this parameter omega, and this is the parameters that derive from experience that we conducted over hundreds of servers, both in Europe and in the US. So here we can see the benefits of using Honus over the the current NTP with respect of the number of servers that are queried per update, and on the percentage of the malicious server in the pool. For example, if we will take the previous case where we have 500 servers and 7 of whom are fully controlled by the attacker, even if we will query 8 servers instead of the 15 that we mentioned before, even querying 8 servers per update, we still improve the NTP by a factor of 100. Notice that the y-axis, the attacker success probability, is on a log scale, which means that the improvement is exponential. And now I will describe our security analysis. If you remember, out of hundreds of servers, M10s are chosen in random, and then D are dropped from each side. So in order to take and analyze the security guarantees we get from Khronos, we need to think of all the scenarios that can happen. Of course, take the worst case scenario, and the scenario are depend on the number of malicious servers that were queried. So our first scenario is when the number of good samples in Yellow Angel is less or equal to D, and the number of our malicious samples in Red Diamond is higher or equal to A minus D. So in our worst case, in our remaining set, we have only malicious server. However, according to our second condition, we set out the malicious servers, the malicious samples average should be close to the client's clock, otherwise we resample. So the maximal shift is bounded. And another thing we have to mention is that the probability of this scenario is extremely low, since it requires that the malicious server samples or servers will be queried in much higher rate than the rate in the population. And of course, with repeated shift is negligible. That is why we can say that a significant time shift here is feasible. The second scenario is the opposite one, is when we have more than D good samples and less than A minus D bad samples. So the first option is when we have only malicious samples in our remaining set. However, since we have more than D good samples, we have at least one good sample from each side of this remaining set. Good samples are within omega away from the UTC, which means that all the samples in our remaining set here are omega away from the UTC, and the average that we use in order to update our clock is omega away from the UTC. The other option is that when we have at least one bad sample, one good sample in our remaining set. However, since we have at least one good sample which is omega away from the UTC, and according to our first condition, all the samples in the remaining set should be close to each other, then all the samples are also close to the UTC, and their average will be close to the UTC. And that is why we can say that these attack strategies are ineffective. However, if we cannot shift time, maybe we can attack differently. So if we have at least D more than D malicious samples, we can insert, and at least one bad sample is within the remaining set. He can violate one of the conditions. For example, the first condition that meant that that stands that all the samples should be close to each other, and then cause a resample again and again and again, k times, until we reach to the panic mode, and causing multiple Khronos client to multiple time reach the panic mode may cause denial of service over the NTP servers. However, even if we set our panic threshold to be extremely low, that we coming to a panic threshold after 3 trials, the probability of success is negligible, which means it will take the attacker decades to force panic mode over one Honus client. Sorry. Another remark I should add is that even if we don't have large pool of servers, for example, in PTP, when we have only say 3 servers or master in PTP, we still can use the Honus that will skim over all the entire pool, and then we can get a deterministic security guarantees instead of probabilistic one. So to conclude, NTP is very vulnerable to time-shifting attacks, especially made by man-in-the-middle, since it wasn't designed to protect against strategic man-in-the-middle, and the attacker who controls even few servers can shift the client's time. That is why we presented a modified NTP client called Honus with provable security, even facing powerful and sophisticated men in the middle. It has backwards capability since there is no need to change anything in the servers, only in the client side. And we had only low computational and communicational overhead since we query only few servers in the end. And these are subjects for further research. If we can achieve security, tighter security bounds, maybe we can weight servers according to their reputation. What can we benefit if we allow also server-side exchanges? And of course, we would like to extend Honus to other protocols such as PTP. Thank you very much. This is linked to our paper, and I can take questions now. Thank you.
Hi, Philip Prindeville, Network Time Foundation. One of the premises you didn't look at was that general computing bases typically have valid real-time clocks on the BMC or the SME set at the factory before they even ship. So why not assume that you have an approximately good time, give or take a few seconds, already set with the real-time clock that's always on, that runs on battery or CMOS discharge.
But okay, maybe I didn't understand the question. You're saying that along with the NTP, I have a good clock. What?
The CMOS real-time clock on most general purpose computing facilities, so servers, desktops, towers, and so forth, gives you base time that's accurate to within a couple of seconds of good time. So it's a valid starting point for discrimination.
By what? But GPS on other instruments, or
no, the factory clock, the BIOS clock that comes on most computers.
Okay, first of all, we didn't consider that we have any other clock synchronization but the NTP. And I know that in the industry, a lot of companies using also GPS, but then they listen to cellular radio and synchronized by us. But still, they have. I mean, even if they're listening to even if they're listening to several cellular networks, then they still have to figure out which one is the best one. I think this is what you're trying to say.
I'm talking about the clock in the computer. I can order online from Amazon a Dell laptop, turn it on, go into BIOS, and it'll show me the correct time within about 2 or 3 seconds of GPS time.
Oh, so it's based on GPS signals?
No.
Okay, maybe we'll get
the clock in the
so you say that we don't need an NTP, or I'm not sure what.
I'm saying it's a good basis for filtering any responses that you get, because your computer boots up as you receive it from the factory with fairly accurate time already programmed into it.
Okay, we refer to the current NTP where I'm not sure that it's this synchronized for you. I mean, if you don't have any NTP server, then yeah, it's use your computer and clock back. Otherwise, it's based on NTP servers. So
I'm saying that time is a good starting point to filter your NTP pool.
So
Okay.
maybe this would be something good to chat about offline.
Okay, sure.
All right, thanks.
I just wanted to add something about this talk. So we've done a bunch of studies on NTP as well, and we do find that a lot of computers will just take NTP time and just adjust their time. So there are different ways that things are built in practice. The other thing I wanted to say, the other comment was maybe you could use the time that is on the local machine as that reference point, because you have that when you compare the average to the reference point, maybe this is another reference point that you can incorporate in the algorithm, which is not necessarily what NTP does at all today. And the other thing was I just wanted to say personally, I really like this work because we have an NTP algorithm that's, Marzullo's algorithm. It's been changed, but Marzullo's algorithm is 1984, so it's extremely exciting to see people looking at this again, kind of to see the best way to build these algorithms. So for people in the space, I think it's really interesting to look at some new research and the ways to actually adjust the client.
Thank you.
Sorry, and all I actually wanted to say was she has agreed to bring this work. She's going to be presenting at the NTP meeting on Wednesday, and so we'll have time to discuss this further. So thank you very much.
Thank you.
So let's thank the presenter. Okay, so last but not least, we've got Amog Damdare from CADA, who's going to be talking about TCP congestion signatures.
All right. Thanks, Philippa. Thanks to the organizers as well for having us, inviting us to present this work here. This paper first appeared at the Internet Measurement Conference last year, and this is joint work with Srikanth, who used to be at Princeton when he did the work, but is now at Facebook, Mark, who's also here, and Casey. So this work was motivated by speed tests, and in particular, the fact that speed tests don't often tell you as much as probably you want to know about throughput. For instance, this is one of the typical, very common speed tests that a lot of people use. This is speedtest.net. So when you go to the website, it directs you to a server that's close by. It does a bunch of upload and download tests. It tells you the ping time to the server. It tells you the download speed and the upload speed, but not a whole lot more. So, for instance, it doesn't tell us what was limiting the throughput of the TCP connection. It doesn't tell us where the bottleneck was. It doesn't tell us what type of congestion did this TCP flow experience. And what do I mean by that? So broadly speaking, if for a TCP flow on an end-to-end path, you can think of two different sort of types of congestion that it may experience. So first of all, you have, say, what we term as self-induced congestion, in which case the flow starts up on a path which is initially, say, clear, and the flow is able to now ramp up and saturate this bottleneck link. So imagine, for instance, a last mile access link, which is mostly empty to begin with. The flow starts up on this link and is able to saturate this link completely. On the other hand, we have the second type, which we term as external congestion. And what happens here is that the flow starts on a path which already has a congested link on somewhere on the path. So the flow isn't actually able to ramp up to the point that it actually saturates a bottleneck on its own. And for instance, this can happen, for instance, if you have a congested interconnect link deeper in the network than the access link. So distinguishing these two types of cases can have some useful implications. So for instance, for users, you'd like to know whether it's the access link that limits your throughput or if it's a link that's further down in the network, and you should talk to your ISPs. For ISPs and content providers, on the other hand, they want to know if the congestion is something that they can route around. And for regulators, finally, if they see evidence of persistent congestion on interconnection links, this is something that they've been interested in the past and sometimes warrants regulatory intervention. So we might think that it should be easy to just look at sort of the throughput numbers that you get from a TCP flow, for instance, from a speed test, and try to figure out what type of congestion that flow experienced. But it turns out that it won't be that easy. Because, for instance, first of all, access plan rates can vary pretty widely. So you can have DSL, say DSL links which are low capacity. You can have higher capacity, cable and fiber links at the home. So, for instance, if you do a speed test and you get 5 megabits per second, what does that say? Is that the access link capacity, or is that the whatever throughput the flow was able to extract out of a path that was already congested? So the idea that we tried to explore in this work was that we can actually use the dynamics of TCP's congestion control, in particular during the startup phase, during slow start, to actually try to figure out what type of congestion that flow might have experienced. And this is what we call congestion signatures. So to go a bit deeper into what we're talking about here. So suppose you have a flow which we're saying it's going to experience self-induced congestion. So what happens in this case is it starts up on the path and tries to fill up an empty buffer during that initial slow start phase, the empty buffer in the bottleneck link, which is trying to saturate. So what's going to happen is that you'll see an increase in the TCP's flow round trip time, especially during that first slow start phase where it's actively probing for bandwidth. On the other hand, if you have a flow that's externally congested, so meaning that it starts up on a path that's already congested, there's less potential for this flow to actually drive buffering behavior at that bottleneck link. So what's going to happen here is that there's less of a potential for an RTT increase during that initial phase where the flow is probing for bandwidth. So to put these two together, if you look at the difference between self-induced congestion and this external congestion, what you'll find is that the self-induced congestion will tend to have a higher RTT variance during the slow start phase as compared to external congestion. And the idea is that we can actually quantify this difference between these behaviors using two very simple metrics: the maximum minus the minimum of the flow RTT during slow start, and another metric thrown in, the coefficient of variation of RTT samples that you collect also during slow start. So to see if any of this holds any water, we did a very simple controlled experiment using a test bed, which I'll describe in just a little bit. But essentially what we did was to simulate different configurations of an access link, in this case with a 20 megabits per second capacity, 100 millisecond buffer, and an interconnect link for deeper down in the network. And we did various configurations of flows that were either self-limited or externally limited. And because this is a controlled test bed experiment, we know exactly which is which, so we can label them accordingly. And then we look at these two metrics that I talked about, the maximum minus the minimum RTT. And in this case, actually, it's the normalized max minus min, normalized by the minimum, and the coefficient of variation of the RTT during the slow start phase. So without going into too much detail, the CDFs are basically, the blue line is for the self-induced flows and the red line is for the externally congested flows. It's pretty clear that in both cases, for the maximum minus the minimum and the coefficient of variation of the RTT, the self-induced the flows with self-induced congestion have a much higher value of these two metrics as compared to the externally limited flows. And it's just not, it's not like just a little bit higher or something. You can see a pretty qualitative difference between these two behaviors here. So the idea was that to try to leverage this qualitative difference between the two types of congestion to actually try to differentiate them using these statistics that we can collect. So the model that we built was pretty simple. We have these two metrics which I just described, the maximum minus the minimum of RTT normalized, and the coefficient of variation of RTT. We built a simple decision tree classifier. We trained this using ground truth labels that we are able to collect in a test bed setting. And then we try to apply the resulting model to try to classify flows into one of these two categories as either being self-limited or externally limited. So as a first step to first of all building the model and sort of validating it in a very, very controlled setting, we have this test bed here. Without going into too much detail, it's a small scale test bed in a lab where we have two sort of core routers and a bunch of edge devices at the edge, which are Raspberry Pis, generating the traffic and the throughput flows and so on. We generate cross traffic to saturate the interconnect link and throughput test from one of the edge devices to servers that are on the internet. So the good thing about doing this in a very controlled lab environment is that we can explore a wide range of access link throughputs, buffer sizes, loss rates, different types of cross traffic with different configurations of how loaded the interconnect link versus the access link are, and so on. And the other good thing is we can exactly label the flows as being experiencing self-induced congestion versus external congestion because we have all the data, so we kind of have the ground truth in this case. So when we build a model, the decision tree model that I described earlier, using just these two very simple metrics, and we apply it to sort of a half of the data that we collect from the setting, we get pretty good numbers. For most configurations of these different parameters, we're able to get a precision and recall that are both greater than 90%. So it seems to work in general. So to take it a little bit further, we try to test this method out in a setting that was a little less controlled than our lab environment. And for this, what we did was to leverage some infrastructure and data that we're collecting from another project that's ongoing at CADA. And the idea of that project is to actually try to measure interdomain congestion, so congestion at the borders between networks. So imagine two ISPs, A and B. In one of the ISPs, we have one of CADA's Archipelago or ARC vantage points. These are boxes that we give to people. People host them voluntarily in their homes. We can do a bunch of measurements from these boxes. So for instance, if from this ARC box, we're able to identify an interdomain link with a neighboring ISP B. Right? And now if we want to figure out whether this link is actually congested, at a very high level, what we do is from this ARC box that's inside the ISP, we do latency measurements to the near side router and to the far side router. We do this continuously over time. And we look at the time series that results. And if you see a time series to the far side router that looks something like this, which is basically showing diurnal latency elevation. So if you look at this graph, this is a month long. Each of those spikes happens pretty much every day. It's a couple of hours every day. This indicates that the latency elevation during peak hours is due to the queues in the router filling up, and that link is actually congested during peak times. So this gives us a method to identify links that are actually congested, that are deeper in the network. This is an interdomain link between two ISPs. There's, of course, a lot more to this method than I just described. In fact, we have a paper coming up at SIGCOMM later this year that describes the whole method and some other data that we've collected. But for the purposes of this study, we used, we were able to run this method, find a congested link between two ISPs, one of which we had a vantage point inside. And now what we did was we looked for an MLab NDT server that was behind this congested link in the sense that when we ran a throughput test from the NDT server to our ARC VP, it would actually traverse that congested link. And we did a bunch of throughput measurements over time. So if we look at the throughput measurements, the download throughput that we get from this NDT server over time and try to correlate it with the elevated latency to the far side of the interdomain link, which I was showing earlier, happily enough, there's a nice negative correlation. Basically, whenever the latency-based method indicates that that link is congested, we get much less throughput across that link than we would if the link was not congested. So using these results, we can basically say that these data points over there that correspond with the down spike in the throughput that happen when that link is congested are actually externally congested flows, because these flows are actually bottlenecked by that interconnect link and not by the access link of the user. On the other hand, if you have these data points way at the top over there between 25 and 30 megabits per second, which was the capacity of that user, it's pretty safe to say that these are self-congested flows at that point. So using our model to now try to classify these and see what our model says about them, we actually do a pretty good job. So in terms of detecting the externally congested flows, we're able to get more than 75% accuracy. In terms of detecting the self-induced congestion flows, we're actually much better. We get close to 100% accuracy. So finally, with we took one further step to sort of try to test this out in a setting that was now completely uncontrolled in every sense of the word. So for this test, we used entity data that comes from MLab. And for those of you who are not familiar with this, MLab runs a large server-side infrastructure against which people run entity tests, and they collect all that data, and it amounts to thousands and thousands of tests every day. In particular, we focused on one time frame in the 2013 and 2014 period, when what people were finding was that NDT tests from various different access ISPs to servers in Cogent and some other networks were showing significantly lower throughput during peak hours than during off-peak hours. And a lot of the major ISPs in the US, like Comcast, Time Warner, Verizon, and so on, were affected by these diurnal throughput issues. Cox was actually one of the notable US ISPs that was not affected, and this will become important in a little bit. And the underlying cause for these performance degradations turned out to be congested interconnects between Cogent and a bunch of these different access ISPs. So this is what a throughput graph looks like. If you look at hourly throughput between a Cogent server and various different access ISPs, this is in January 2014. You can see that clear diurnal dip during the peak hours when the throughput to Comcast, Time Warner, and Verizon dipped significantly as compared to during off-peak hours. Note that Cox, which as I was saying earlier, was not affected by these interconnection disputes, doesn't actually show much of this kind of a diurnal pattern. On the other hand, by April 2014, many of these interconnection disputes had been resolved in one way or the other, and we won't go into that here. But basically what happened was, if you looked at that same sort of throughput thing over time, it's basically you don't see so much of a diurnal dip in that throughput anymore. So what we did was, let's say during this time frame when these interconnection disputes were happening, we can say that the flows that we collected during the peak hours were likely to be externally congested. And on the other hand, after these disputes were resolved, the flows that we were collecting were likely to not be externally congested. So they should be self-inducing congestion. But this data is noisy. In fact, we had a paper at the same IMC last year actually saying how noisy this data was and how difficult it is to actually infer that there's a problem at an interconnect based just on these throughput tests. So we're not going to expect that all the flows that we label as being externally congested are going to traverse congested interconnects. Also, we don't expect to identify all the peak hour flows as externally congested. So basically what I'm saying is, whoa. Okay. Okay, that should wake everyone up. So basically what I'm saying is this labeling is not going to be perfect. We're going to look for sort of qualitative differences between the two time frames in terms of what our technique can actually classify the flows as being self or externally limited. So let's see what it actually shows us. So the way we did this was for each of the different time frames, so January, February, when the interconnection disputes were happening, this is all the red bars, and March, April timeframe when the interconnection disputes were resolved, we looked at the fraction of tests that we were classifying as being self-induced in each of these time frames for different combinations of the server, which was Cogent and level 3, and access ISPs, Comcast, Time Warner, and Cox. So first of all, if you look at, for instance, the Cogent servers to ISPs like Comcast, Time Warner, and Verizon, you'll find a much lower incidence of self-induced congestion during the Jan-Feb timeframe as compared to the March and April timeframe. This is what you would expect. If the interconnection disputes were resolved, you should find a lot more of the flows as experiencing self-induced congestion. On the other hand, level 3, which wasn't actually significantly affected by these interconnection disputes, didn't show much of a trend over these two different timeframes. Again, like I was saying earlier, Cox was not a part of this dispute. Again, you can look at those two bars corresponding to Cox and find that there's very little difference between the two timeframes according to the technique. So basically, this gives us some confidence that the model that we have is actually able to classify flows into the self-induced and externally limited categories with reasonable with confidence. Now, there's a lot more to this in the paper. I don't have time to go into a lot of the results, but if you're interested in sort of more details about how we build the model and how we apply the model to different data sets and so on, all the details are in the paper. So I want to conclude by taking just a few minutes to talk about some follow-on work that we've been doing, sort of as follow-on to this idea, but more in the spirit of sort of these in-band measurements. So the idea is kind of simple. So we have an ongoing TCP connection. Can we actually try to leverage this TCP connection to do some sort of path measurements? So for instance, the signatures technique that I just talked about says that a flow is likely to be either self-limited congestion or externally limited, but it doesn't say exactly where that bottleneck is. So for instance, can we actually try to figure out where that connection is bottleneck? What is the available capacity or bandwidth on that path and so on? Why in-band measurements? So the idea of in-band measurements is that you don't want to be sending external flows to do the measurement because they could be routed differently, treated differently by intermediate boxes and so on and so forth. So you want to be able to do measurements that are within the flow that's actually you're trying to measure. So another advantage is that if you're looking from the server side to say a client in a home, the TCP flow has already actually punched a hole in the NAT. So by leveraging the existing connection, you can actually traverse the NAT and measure all the way to the client. So this is the kind of the idea that we're playing with. So you have a server and it has an ongoing TCP connection with the client, and you have a program, TCP trace we call it, that sits at the server side. It listens to packets, and now it can actually inject packets into this TCP stream. And you can do all kinds of things that you want at this point. You can send packets that are TTL limited, so that expire at intermediate hops, and you can trace the path. You can send packet trains. You can send packet, packet pairs. You can send empty packets. You can send large packets. You can do all kinds of measurements with this kind of basic approach. And all of these packets are in-band measurement packets, so they are treated the same as the existing TCP flow would be. So what we have so far is a very simple implementation of a high-frequency trace route. So basically, you have a TCP connection, TCP trace latches onto that connection, sends empty packets continuously at a high frequency, and if you pair it with basically a speed test kind of flow at the server side, you can find quite interesting things like, we can actually observe the buffer building up at the bottleneck hop. You can actually measure all the way to the client, pass the NAT, observe wireless delays, and so on. We have a basic implementation up here. So if you'd like to play with it, modify it, whatever, you should ask us for access. Finally, just very quickly, we have some work in more work that we're currently working on, basically with the same idea, but trying to do more complicated measurements, not just a trace route in band, but something more complicated like packet pair and packet train techniques to measure per hop capacity, available bandwidth, loss rate, and so on and so forth. One of the major sort of engineering challenges that we're dealing with at the moment is to try to utilize packets from the existing TCP stream and also sort of intelligently inject our own measurement packets in a way that first of all, doesn't affect the ongoing flow, and then trying to get all the timing issues right and so on to get actually the measurement that we're trying to get. So that's sort of the status of where we are at. I'll be happy to talk more with anyone who's interested offline. That's more or less what I had. Thanks very much, and happy to take questions.
Thank you, Amok. That was a very interesting talk. Two things. The first thing is that the graph that you showed, that showed the self-induced condition versus other. I think you may be making some assumptions, and I want to try and get to those. What is the condition controller that's being used on those traces? Do you know?
This is the default for Linux. These are Linux.
You lost your mic.
Oh.
Just for the remote part.
All right. So this would be the default in Linux. So cubic.
So it would be cubic. Yeah. Okay. So it's probably cubic with high start in that case, I'm assuming.
Okay. Yeah.
Which I'm surprised. Okay. So there are two things that contribute to that difference, I would say. One of them is that there is a deep buffer in the network. The second, is that the sender will saturate the deep buffer.
Right.
And those two assumptions have been challenged over the past couple of years and are continuing to get challenged. Specifically, the deep buffer question with increased AQM deployment, you should see lesser of that in the network. Yeah. And the second one is with congestion controllers like BBR or other ones that are getting deployed increasingly, you should see lesser again behaviors that seem to be reflective of the graph that you showed there. I'm sure you've thought about this, so I'm curious to hear what you say, and then I'll give you my second one.
Yeah. So like I was saying, we did actually experiment with various different configurations of that buffer size, and you're absolutely right in the sense that if you get really small with the buffer, then the ability to distinguish these two scenarios diminishes because it relies on the fact that there's buffering. But in the sort of space that we explored, we found that we were able to do a pretty good job, and we didn't try AQM. So that's another fair point. I mean, with AQM, again, the difference between the delays is likely to get smaller and harder to distinguish. We also didn't look into some more of the modern congestion control variants like BBR, but that's something that we've been wanting to look into. Just haven't had cycles.
I'd be very curious to see how this looks with that.
Yeah.
Also, because I think there's a question hidden in what you're doing here, which is even for an endpoint to be able to detect if it's actually if it can look at its own delay signatures and figure out if it's competing with another flow in the network. That's a huge thing it's information that an endpoint can use to good effect.
Yeah.
A BBR flow, for example, does have trouble competing sometimes with cubic, and then that's something that it could use to good effect. So that's something that
absolutely. That's the BPR was on our sort of to-do list as a follow-up. We haven't gotten to it yet.
Yeah. So I would very much appreciate any follow-up work on that. Second one, suggestion on the naming. TCP trace is taken.
Oh, okay.
We all love Sean Osterman's tool.
You're right.
So I would, if it's not too late,
so
consider a different name.
So this is actually. Did I call it TCP trace? The repo is trace TCP.
Yeah, well, that's equally confusing.
And now we're actually calling it buffer trace. So it's fine.
Thank you again.
Okay.
Hi, thank you for your talk. Maria Postolaki from ETH Zurich. I wanted to ask whether you could elaborate more on why we actually see this difference in the delays and what actually causing it. What is the difference? Why we see more variance in one case? Like right. I didn't get that. Maybe.
Right. So basically, what is happening is that when you have a flow that starts up on a path. So imagine a flow that starts up on an access link that's mostly empty to begin with, right? And it's going to try to saturate the first bottleneck that it hits, and in doing so, it's going to fill up the bottleneck and also start filling up that buffer. And that the filling up of the buffer is what contributes to inflating its own latency in some sense. So that is basically, if you look at the RTT of that flow when the flow starts and when it hits the first loss, say, there's going to be a big difference because it has had the opportunity to fill up a buffer and inflate its RTT. On the other hand, if you have a flow that's already externally limited, that link is full, that buffer is also partially or fully occupied. So there's very little scope for that flow to actually now drive buffering behavior and increase its flow RTT. So the RTT from the time it starts to the time when it experiences the first loss is not going to be that different. That's the effect that we're seeing.
What if you have bursts? So like in this case, your buffer would go up and down in a way that you would not be able to predict. So it might kind of mess with your signal.
Right. So that's why that's why we use these two different metrics, which is the max minus the min and the coefficient of variation. So what the coefficient of variation is doing is looking at sort of how much is bouncing around, that RTT is bouncing around during that time. Yeah.
Thank you very much.
Okay, so we've got a question from the Echo. So I just hit this red button here.
That's the internet.
Can you please unmute your microphone?
Are you muted, Spencer? Would you email your question maybe and we can relay it?
Can you hear anything from here? No.
Are there any more questions while we? Maybe we should just catch them. All right. So thanks everyone.
Write down my email address over there.
Okay.
Thanks
everyone.
See if nothing else going to press that button. Cool.
You see that IT crowd.
Just a note that we're back at 3:50.